Welcome to our presentation on faster kernel matrix algebra via density estimation. The topic of this work is matrix operations in data analysis and machine learning. They are very fundamental, they come up all the time, and they pose a major computational bottleneck. As a result, a lot of effort is being dedicated to speeding them up on several fronts. So there is the hardware front and the software front, and in this work we are going to be concerned with the algorithmic front. So our goal is to develop asymptotically faster algorithms for those problems. And here we run into a natural barrier, because just reading the content of an n by n matrix takes n squared time, which doesn't scale well. So in order to circumvent this barrier, we are going to rely on the fact that many times our matrices come from data. So if we have, for example, a data set of objects like images or text or anything else, we usually map them into high-dimensional feature vectors, and then the matrix is defined based on those vectors. Specifically here, we are going to work with kernel matrices. So a kernel is just a measure of similarity between points in R to the d. It takes a pair of points and measures their similarity as a number between 0 and 1. And here are some examples of popular kernels that are often used. And if we have a dataset x1 to xn in R to the d, then the associated kernel matrix is naturally defined as the n by n matrix that contains all of the pair similarities between the points in the dataset. So what we do in this work is leverage some recent work on fast data structures for the kernel density estimation problem, or KDE, in order to get fast linear algebraic algorithms for those kernel matrices. Specifically, we are going to look at two matrix operations. The first is estimating the sum of all entries in the matrix, up to a 1 plus minus epsilon approximation. This has applications to the kernel alignment problem, and our result here is a sublinear time algorithm. So it runs in time asymptotically faster than n. And the second problem we are going to look at is approximating the top eigenvalue and eigenvector of the kernel matrix, meaning finding a unit vector z such that the value of the quadratic form that it forms with the kernel matrix is almost as large as it can be, which is the top eigenvalue of the matrix. This has applications to kernel PCA, and the result here is a subquadratic time algorithm. So it runs in time asymptotically faster than n squared. More concretely, these are the bounds that we get for the different kernels mentioned earlier. Now, as we said, what we do here is transform existing data structures for KDE into matrix algorithms, and the currently known complexity of KDE for each one of those kernels is somewhat different, and this is why we get different bounds for them. So in the middle column, you can see the reference for the fast KDE data structure that we use for each kernel. In the blue column, you can see our running times for the kernel sum problem. They are asymptotically faster than n, and close to the lower bound, which is square root of n. And in the purple column, you can see our running times for the top eigenvector and eigenvalue problem, asymptotically faster than n squared, and close to the lower bound, which is n. Now, let's have a quick overview of our method for the second problem, for the approximation of the top eigenvector and eigenvalue problem. Our method is called the kernel noisy power method, and it works roughly as follows. A convenient way to approximate the top eigenvector of a matrix is by the power method, which is a sequence of matrix vector multiplication operations, or MVMs, starting from some arbitrary or maybe random vector. And if the matrix is a kernel matrix, then each one of those MVM operations can be approximated by a sequence of kernel density estimation operations, or KDE. Now we can use some recent work for fast data structures for KDE based on locality sensitive hashing, which is a powerful technique to get fast approximation algorithms for points in a high-dimensional space. And what we get in the end is a noisy version of the power method, where in each step the MVM operation is not exact, it has some error. And there has been past work on noisy power methods, but those works assumed that the noise was random. And in our case, the noise is not random, it can be worst case, so it requires a different analysis that relies on specific properties of kernel matrices. Finally, let's see some experimental results. So here again, we look at the approximation of the top eigenvalue and eigenvector problem. On the x-axis, you can see the number of kernel evaluations that each one of the methods performs. So this is the number of entries of the kernel matrix that the method reads, and this is a proxy for the running time. And on the y-axis, the relative error is just epsilon from the problem definition. The methods we compare are, in blue is the full power method. As you can see, it is very slow. In green, uniform is a baseline based on uniformly random sampling. It is not asymptotically faster than the full power method, but as you can see, it is empirically much faster. And in red, kernel noisy power method, our method is even faster in converging to the top eigenvector and eigenvalue. And this is it. For more, please see our paper, and thank you for watching.